is Megan Uninsky, and I am going to present the paper on an experimental study of GPS spoofing and takeover attacks on UAVs. I'm a master's in electrical and computer engineering student, and this is for 8813 Cyber Physical Systems Security. I'd like to start off by acknowledging the authors and this paper. It's published by two at Northeastern University, as well as part of the Swiss arm of Science and Technology. And the authors presented this paper in August 22 in Boston, Massachusetts at the Security Symposium. I've included a link to the paper as well if you would like to reference that. Getting into the key objectives and motivation for this paper, starting off that the UAV market, especially in 2022 when this paper was published, was growing very fast across a wide range of industries, including those with critical infrastructures, including military, civilian, and commercial sectors, and the use cases of surveillance, reconnaissance, delivery and supply chain, photography, agriculture, and many others raise security concerns as more UAV usage allowed more exposure to critical security threats. Importantly, the heavy reliance on GPS by UAVs, unmanned aerial vehicles, creates a single failure breakpoint under GPS spoofing. So if GPS spoofing has high capability of success, then that's a single point of failure for the security of these UAV systems. For a little background, GPS stands for Global Positioning System, and the PNT is the data point it defines, so that's going to be the position, navigation, and timing data, and that's done by using orbiting satellites and wireless communication signals to send the data most accurately as possible from the GPS to the UAV. Let me briefly explain GPS spoofing. GPS signals are unencrypted and they lack authentication, which allows adversaries to send counterfeit signals. UAVs receiving these fake signals calculate incorrect positions, potentially steering the UAV off course. This research indicates whether or not it is feasible to control a UAV fully by using only GPS spoofing, which is a step beyond prior simulation-based studies. This GPS spoofing is done at the physical layer, where the adversary sends the counterfeit signal and the receiver then calculates the PNT point data. And then the spoofed location can become known as the actual location and actually move the UAV off course. There is no authentication, which is critical, and there's public access to these system designs for the UAV as well as communication protocols. Overall, the main goal of this paper is to not only look at whether or not GPS spoofing is enough to gain full control, but what is meant by full control of a UAV. How feasible is it for an attacker? What are the requirements? And what are the limitations for the spoofing control? So is the risk as high as anticipated as UAVs enter these critical infrastructure use cases? Importantly, the prior work did not include this real-world field testing data and experimentation. It was more simulation-based. Firstly, I want to discuss the flight controller architecture that was used in these tests. These tests and experiments were done with commercial-based UAVs, which contain PID controllers, sensors, which are going to be critical components, as well as actuators, and the GPS, again, is heavily relied upon when the architecture is used in autonomous mode. The paper discusses autonomous mode mostly, and this is opposed to manual mode where the operator remains in full control. Understanding this flight controller is critical because in autonomous mode, UAVs rely most heavily on the GPS and things like inertial measurement units and vision sensors that are integrated through the PID controller. And this is important because it'll manage position and altitude. Spoofing GPS signals directly interfaces with this command and control loop, which particularly when GPS is prioritized over other sensors. And this is going to be really where the feasibility aspect comes in because of the different parts of the control loop. The attacker is going to need to work with real-time data and create changes in order to fully gain control. Importantly, we'd like to define now what capabilities the adversary has in order to determine feasibility of threat and look into deeper about how this system can be exploited. So in this paper, we assume that the attacker can generate and transmit these GPS signals, meaning that the UAV must be within the attacker's range of radio signals. And this is done by spoofing the GPS signal. So GPS spoofing is going to be the main means of exploitation in this paper. And with that being said, the attacker remains primarily focused on forcing the UAV to move to a specific location, the spoof location. Additionally, we assume that the attacker has taken over the UAV's GPS receiver. In order to do so, there is two main techniques used in order to assume that the GPS receiver has been successfully attacked. These go into detail through other papers, but very briefly they include the overshadow attack, where a fake signal is sent that is so powerful it is enough to bury the real signals and basically act as the real signal, and this is easily detectable. So a more stealthy approach would be enabling synchronization with the real satellite signals and slowly adding code offsets through the spoof signal that make the receiver move from its actual location more slowly over time, instead of it being so powerful at once that it's easily detected. Importantly, the field test and design experiment setup needed to accommodate all of the different abilities in order to wirelessly transmit the spoofing signals securely. And a high precision real-time monitoring environment was also necessary so that you could precisely track the UAV's movement. Because of the reliance on the control loop for the attacker to successfully gain control, in order monitoring it in real time with high precision is extremely important. This chamber that was used also needed to absorb sound in electromagnetic waves without any echoes or reflections to ensure the wireless communications could be taken on. Additionally, safety was important, and a 24 OptiTrack camera motion capture system was also included. This made sure that it created an environment that the signals could be spoofed. Additionally, this image here shows the other equipment, which include the GPS TX transmitter controller, as well as the antenna. And this shows the consumer DJI UAV that was used. Here is the control panel in the middle showing what is like video game controls that the attacker will be able to use. Additionally, power amplifiers and SDR software-defined radios were used as well. So this shows visually what this experiment setup looks like. And in a little more detail, this shows the variety of different DJI models of UAVs that were used in this test. The leading manufacturers are DJI is one of them, so this is sort of a realistic use case for the model being tested, as it has majority of the market share. The first initial experiments were static and dynamic spoofing location. So in the most simple case, the static location spoofing, what the experimenters did was the drone was set to just hover, and what you first wanted to do was send the spoofing signal to be the exact same location that where it's set to hovering. This caused the UAV to drift and move randomly due to some inertial sensor bias. So these sensors in the architecture are highly critical, and there's so many of them that it does not make it as easy as anticipated for the attacker. So even by spoofing the exact same location, the UAV was drift and randomly moved. In the second case, in dynamic spoof location, in this experiment, the UAV direction of motion shifted by 180 degrees. So this will be, going to the next slide, when we spoofed this direction towards point B from A, the UAV actually moved in the direction of C. And the PID controller needed to compensate for the error between the desired and actual position. And during this compensation period, it caused the UAV to actually start accelerating, which will be critical for the attacker to need to compensate for over time with the real-time monitoring of the drone to be able to successfully gain full control. And we are going to define what that full control means. So here shows some of the data showing that the acceleration becomes about 0, and then all of a sudden it goes negative and then positive again as it's trying to compensate of the different directions as it's pulled 180 degrees when dynamic location is spoofed. Again, the attacker no longer has control over the speed or direction of the UAV. So when this acceleration is introduced, attacker does not have any control. And this, what the experimenter saw was the UAV battery at this point will either deplete or the UAV will crash and cause termination of this experiment. Even if the spoof trajectory direction is changed, there is still no control that allows the UAV to change direction. So from this point, when it flips 180 degrees, there is no real control anymore for the attacker. So most importantly, these two experiments, even though they are just dynamic and static spoofing, it allowed them to decide on what it really meant for control. What are the conditions for complete UAV control? And they came up with 3. So the first is that the attacker must have control of the UAV direction. The second is that the attacker must have control over the UAV speed. And the attacker must be able to land the UAV. So this last one accounts for the case where when there's no longer control, it's just waiting on battery depletion or some type of crash to happen. And this clearly is not full control over the device anymore. So the first problem, the researchers investigated how to ensure that the UAV's velocity control. Could the attacker maintain control of the velocity? And the UAV, the problem here is what we saw in the dynamic spoofing is when the UAV responds to the spoofing, it starts to accelerate in the opposite direction. In this, the controller must correlate and compensate due to this change. And what's important with that is that over time, the compensations become more and more. So, for example, as the change occurs and if the UAV starts moving in the other direction, it gets further and further and further from the actual point it's supposed to be at, so that it starts accelerating even more and even more. So what the researchers aim to do is they want to make the controller believe that the corrections are actually working. Because when they start working, that difference in spoofed and real location become more and more. So the corrections become more and more, and the controller starts accelerating more and more, which leads to a loss of control. And in order to stop that, they want to target the controller and make it believe that the corrections start working, so that it'll actually do the opposite. The accelerations and compensations will become less critical over time. So in order to do this, they targeted what they wanted to define as the deceleration phase. So instead of when the difference becomes high between spoof and actual location, instead of accelerating more and more because the compensations aren't working, they wanted to do something called an RTL, which is a return to launch maneuver. And what this maneuver is it's reversing the spoofed motion's direction periodically so that the differences stabilize over time. And in order to reverse this direction periodically, the lag time, or the UAV's reaction time, which is defined as the acceleration time to achieve the target velocity, was used. So what the researchers did was they applied the return to launch maneuver which is reversing the spoof's motion directly, where the spoof trajectory approaches the initial position versus away from it. So what this allowed them to do was allow the new spoof velocity changed by 180 degrees. So they changed it again, and this caused the deceleration. So you can see this here. So as you can see, the velocity is becoming going up, and then it decreases, which causes this deceleration phase, and then they change it again, and over time the spoofed and actual velocity finally overlap. So what they did was, with this data, they performed 48 flight tests, and what they wanted to do was maintain an average acceleration of 0 meters per second squared. And they wanted to do that because the attacker no longer has control when the acceleration starts. So if the acceleration's kept to 0, then they make that condition, they check that condition because the control is still maintained. And they also wanted to limit the speed to about 0.5 meter per second. And overall, these tests were largely successful, as over 81% of the flights maintained that low average velocity, and over half of them had near zero acceleration. And this chart shows the acceleration, and as you can see, it's pretty close to zero for the 48 flights. And as well as this is the velocity in meters per second. Without the velocity control, you can see that it starts increasing and increasing at a faster rate. So this is where in orange you would have that acceleration and lack of control, where you're just waiting for the UAV to crash. However, with this new control mechanism, where you're changing the spoof direction, you can see that it's much more constant over time, nearing that less than 0.5 meter per second mark. Delving into the second main point for having full control is having control of the direction. So the main problem here is that the direction is not controlled by the attacker by only changing the direction of the spoof motion. So the flight controller is already performing that correction, just like we saw in the velocity problem, that the attacker can't just change the direction and have it go where it needs to. So in order to solve this problem, you needed to again add this deceleration in order to cancel the corrections that the PID controller is making, as the difference between spoofed and actual location becomes less or more. And then you needed to change the direction of the spoof motion again to have that direction control. So as you can see in this example here, the direction is changed by 90 degrees as the attacker forces that 90-degree turn. That allows the drone to start going east and then up again. And this was solved by something called an HITL in the GPS spoofing, which is human in the loop. And the problem that was addressed by adding the human in the loop GPS spoofing was that using the UAV reaction time to accelerations and decelerations is unreliable. So the UAV reaction time is this lag time, which is the time to accelerate in order to achieve the target velocity. So the researchers found that that's not reliable, and when you apply the direction reversal just at that time, it doesn't always work, basically. So the human in the loop basically adds feedback depending on the UAV's reaction to GPS spoofing. So this goes into more of the real-time monitoring, which is why the environment of these tests had such high capability monitoring software, because the UAV's motion can then be monitored by the attacker. And this human-in-the-loop device is used to manipulate the UAV trajectory. And this is going to be similar to the video game controls, like seen here in this middle control panel, where you are actually, like in a video game, controlling the UAV trajectory. An example of this would be the attacker using arrow keys to control the direction of the spoofing signal, or manual control being enabled for the UAV, which maintains control. So this, when you have the human in the loop, the attacker is manually controlling for landing. And now for the third problem of full control of this UAV is the landing. So what we previously saw was, because of the high acceleration that keep increasing as the controller architecture starts compensating more and more as the initial compensations don't work, it basically just keeps going until the UAV will crash or have a loss of power. In order to maintain control, and doing this by having a safe landing, these existing fail-safes were used for when the controller detects the errors causing the safety risks. And these include no-fly zones as well as EKF, internal sensor measurement errors. So when the GPS creates the error or the sensors monitor something, then these fail-safes are going to be used. And this chart here shows the different types of forced landing fail-safes that were tested in each of the models. So you have GPS takeover as well as some forced landing fail-safes that have been tested. And overall, what this did was allowed the landing to take place safely, but it relied heavily on those important sensors in the architecture. Overall, these conclusions based on defining these three different conditions for complete takeover UAV made it so they are all vulnerable to GPS spoofing attacks as shown, but it is not as easy as thought or might have been thought for an attacker to gain full control by having speed, direction, and landing control with just GPS spoofing. And this is because of the complex sensor systems that continuously compensate and can continually do so until loss of control occurs. Additionally, manual control can be achieved with the human-in-the-loop system, which allows the attacker some more capability, assuming it can do so. However, closed-loop feedback must be performed to gain UAV control as the attacker responds to the UAV reactions. So what this means is the attacker must be able to, in real time, respond to the response and these compensations of the controller. So it becomes a much more complex closed-loop feedback system than maybe thought. So overall, this paper showed us that for full control based on the requirements defined by these researchers, it is pretty difficult for an attacker by just using GPS spoofing alone. However, future work, including mobile device spoofing to exploit specific features on a specific DJI model, allow for potentially easier access. And what this mobile device spoofing does is it restricts specific modules on the UAV to autonomous control. So what this does is it basically only works on certain types of models, not specifically autonomous control, so it becomes more of a specific case. And a question that will next come is, how do we defend ourselves from the GPS spoofing attacks? And this includes cryptographic defenses, like preventing the ability for the signal to be forged and even spoofed in the first place. But this also brings the question, how do we prevent relay attacks, even with not allowing the forgery? So for the replay attack would be resending the same signal to the UAV and using the data that is output from monitoring the drone with that specific signal and resending it. And critically, when we add all these cryptographic hardware and softwares, where's the processing overhead going to go on these small devices? And this is the same for hardware defenses like antenna and RF anomaly detection that have the same overhead issue, as well as there being just limitations on the protocols used. So one of them discussed in the paper was the Open Service Network Authentication Protocol. So this is going to be your broadcast wireless communication authentication. This itself is vulnerable to replay attacks. So we would have to go a little bit deeper in the protocols in order to truly gain the optimal security. Thank you for listening, and please let me know if you have any questions. Thank you.